Welcome to a short preview of the metathesis reaction experiment coming up. We'll look mostly in this review at things about completing metathesis reactions, double displacement exchange reactions, writing total ionic equations and net ionic equations. Our hope is that when you come out of this, you'll be able to look at the evidence for metathesis reactions, kind of see what's going on, have a little bit of a motivational thing so you can see some pretty precipitations. We'll look at the idea of spectator ions in solution, including how we figure them out in equations and sort of a visual on what they are. We'll also look at writing net ionic equations for metathesis reactions. And so that's sort of what we'll be looking at in this particular view.
Just to get you in the mood for this, we're going to look at a couple of reactions from beautifulchemistry.net. Here's an example of silver nitrate and sodium chloride making silver chloride. Notice it's written down below as precipitating. That's the white stuff you're seeing. Sodium nitrate is still laying up in the solution as well as in the excess silver ion and chloride ion. Here's one that looks like silver nitrate and sodium thiosulfate, making the silver thiosulfate is yellowish looking precipitate in here. So it goes into silver sulfide. In that case, kind of a darker colored precipitate in the end. We look at this. This is a barium chloride potassium sulfate, similar to one you did in barium chloride and sodium phosphate, different reactants. But down here, the barium phosphate precipitates as a white. And so what we're going to try to do in this particular module is look at a little bit more detail on these reactions to see what happens here. It's important. Here, the silver ion reacts with the chromate to make this orangish, yellowish, greenish type of precipitate you see in there. And I think possibly the last one coming up is the copper. So there's copper sulfate, sodium hydroxide. They react to form this compound here, which has really neat blue color. You can kind of see each time it sort of moves suddenly, that's adding an extra drop to it. You can kind of see it grow and grow and grow. So what we'll be looking at overall are some different types of metathesis reactions, different types we typically see. One is precipitation. That'll be our star. In this whole lab, we'll see more precipitations than anything else. We'll also look a little bit at the formation of a gas as an indication of a metathesis reaction, as well as other types of reactions. We'll look at what happens if they form a weak electrolyte. Those are a little more difficult to observe, but they also can be in the realm of metathesis reactions. We'll spend a little time on completing and balancing metathesis reactions. We'll also spend a little time on writing complete ionic and net ionic equations from those balanced equations up above. So think about metathesis reactions. We'll start with precipitation. It's one that will be most prevalent in this week's experiment. And so we'll start out, and the one I've gotten down here, there's a lot of words on this slide, you don't have to read them all. But if I look inside of here, what's going to happen in this precipitation reaction, I have silver nitrate and I have sodium bromide reacting. They're going to form silver bromide and sodium nitrate. The way to think about this really is that the cations are going to swap places. So silver ion is a cation, sodium ion is a cation. So what's going to happen is my silver ion will come over here and replace my sodium. My sodium kicks over here and replaces my silver. I just swap partners. And so on the right-hand side of this equation, my silver and bromine are now together, and my sodium and nitrate are now together. And so that's the basic function of what happens in a metathesis type of reaction. Visually, if you want a visual on it, here's silver nitrate in solution, sodium bromide in solution, same reaction we just saw. Silver bromide is a solid forming sodium nitrate over here. Think about what happens with silver nitrate being soluble. When you put it in solution, it breaks into silver ions and also breaks into nitrate ions. They're up in solution. They aren't laying on the bottom as a solid. They actually are pretty soluble. And so they're up in solution here. I have my sodium bromide also soluble, and so I have sodium ions and bromide ions up here as well. When I take and I mix this one and pour it into here, or vice versa, either way, I get this over on the right-hand side. And what happens in here is my silver and bromide ions are now kind of connected. They made this silver bromide solid that's sitting in the bottom as a precipitate. And up above, the nitrate ions and sodium ions have nowhere to go. They aren't going to form a precipitate. And so what I end up with is my my nitrate ions I started with here are nitrate ions on this side, just still floating around. My sodium ions here are still just floating around. Those are the ones we call the spectators. They didn't do anything, they just watched the whole time. The guts of this reaction are that silver ion react with bromide ion to get to silver bromide. And we want to be able to write those guts of this reaction. Another type of metathesis reaction you'll see a little bit here today is the formation of gas. The classic example is usually with carbonates. Looks like here's a carbonate ion. If I take HCl and react with sodium carbonate, I'll form carbonic acid and sodium chloride, just swapping partners again. The carbonic acid typically will break into water and into carbon dioxide. You'll see carbon dioxide bubbling out in some of these types of reactions.
And the last one we'll look at is just formation of weak electrolyte. And we're not going to say much about this one because we don't really see it very well. But if I start with sodium fluoride and HCl, when I undergo the metathesis, the hydrogen goes with the fluorine, the sodium goes with the chlorine, and it looks something like this. The HF you form is a weak electrolyte. So these actually stuck together. You've made a chemical change here, but you don't really see it as such. There's nothing visual to see about this one. You might be able to pick up a little bit of heat, you might be able to pick those types of things, but you're not going to see it in this particular experiment. When it comes to completing and balancing metathesis reactions, this is a case where you're given a couple of reactants and you're asked to say, hey, what are the products going to be and what's the balanced equation look like? And to do that, there's a couple of things that you have to recognize. One is you're already familiar with writing formulas. You ought to be familiar with writing formulas by now because that's going to help you a lot. If you don't know how to write formulas, then you need to go back and relearn that because you're going to need that to be able to finish these things up. Second thing, be familiar with your polyatomic ions because they're actually, in these types of reactions, they're going to stay together. A phosphate, a PO4, will always be a PO4, a phosphate on both sides. A sulfate will always be an SO4 on both sides. So once you know those stay the same. And then you have to be able to balance chemical equations to find out that wasn't too bad probably before. And so the following slide we'll do is look at the steps in completing and balancing such a metathesis type of reaction. So in the steps, what we're going to think about is, first, we swap the cations around to make our products, and we carry over the subscripts that are part of the polyatomic ion. So sulfate's SO4, the 4 comes over. Phosphate's PO4, the 4 comes over. Carbonate's CO3, 2, it comes over. You do not carry over the subscripts that are for monatomic ions. So, for example, barium chloride, BaCl2, that 2 doesn't come over. You're just making chloride ions on the other side. Go back and think about the picture in solution. In the picture in solution, the sodium ions and nitrate ions were up free on their own. They weren't attached to anything else. And then you write the correct formulas for the products you've made by going back to what you knew from earlier in the semester. You want to balance the equation. It should be pretty easy if you've gotten the formulas correct. And then you indicate the physical state, whether it's a solid, liquid, gas, or aqueous. The difference between liquid and aqueous is aqueous means it's something dissolved in water. Liquid means it's a liquid material. So water itself is a liquid material, but when I put something in it, that stuff is going to be listed as aqueous. This link is a lie. Don't worry about that. You can't do it anyway. But you will find summary solubility rules both in your textbook and also in the back of the lab book, the same set of rules. So let's try this one and see what happens. We're going to take sodium phosphate and barium chloride. This may look roughly familiar. We did a limiting reactant problem with this approach earlier. And so we're going to start over here. We want to get all the way down to completing and balancing this equation. So the first thing I think about is swapping cations. So my sodium comes over and takes the place of barium. Barium comes over and takes the place of sodium. And my initial thought about products is I have sodium stuck together with chlorine. I have barium stuck together with phosphate. That's all we've done is swapped places. Notice I did not carry the 3 for sodium over. I did not carry the 2 for chlorine over. I did carry the 4 for phosphate because he's a polyatomic ion. I go to the second step. What I want to do now is make sure I write these formulas correctly. So I go back to my formula writing expertise. Sodium's in group 1, so he has a +1 charge. Chlorine's in group 17, has a -1 charge. So the formula for this will be NaCl. In barium phosphate, the barium's in group 2, has a +2, and you may remember the phosphate's a polyatomic ion with a 3- charge. So when I think about that and do my crossover method, I'll take 3 barium and I'll take 2 phosphate to make that thing work. So those are my balanced formulas. In the third step, now I need to balance the equation. This shouldn't be too bad. When I look at my equation up here, notice that I've got, glance here, is 3 sodium, there's a sodium over there, but notice I've got a phosphate here and 2 phosphates there. Let's fix that and put a 2 phosphates in front of my sodium here. I'm sorry, a 2 in front of my sodium phosphate. Looks like this. That gives me 2 times 3 is 6 sodiums over here. To get 6 sodiums on the other side, I have to put a 6 in front of sodium chloride. But now I've got 6 chlorines. Well, come back here. How do I fix that? If I put a 3 in front of this, I have 6 chlorines, and now I'm balanced. Okay, so it's fairly easy to balance. If you're having trouble balancing your equation, check carefully and make sure you haven't corked the formulas. Make sure you've got those correct. And now in the fourth step, we go through and we think about, okay, what are we going to do inside of here? Well, we're going to figure out who's soluble and who's not soluble. Who's a strong electron? Who's going to get broken? Sorry, not there yet. Who's soluble and not soluble? And so my sodium chloride is soluble because all the sodium salts are soluble. And my barium phosphate is insoluble because the phosphates are insoluble except for the group 1 and ammonium, and he's not one of those. So he's going to be a solid sitting on the bottom. Another busy slide, but here's the goal on here, is to get to complete ionic and net ionic equations. I want to write out I want to break compounds into their ions if they are both soluble and a strong electrolyte. It has to be both criteria, not one or the other, but both of them. If it fails either one of those tests, it's going to be written as the intact compound. There are ways you can think about this as a flow chart. I'll show you in the next page. And so what happens is I think about acids, bases, and salts. When I look at the flow chart like this, it says, okay, go through your equation and pick out one of the compounds you want to look at. Decide if it's an acid, a base, a salt, or a gas. Okay. And based on that decision, you come to the right. If I'm, say I had a salt, I come over here, it says it's a soluble salt. And if the answer is yes, I'm going to take and break it apart into ions. If not, I'm going to leave it intact. And so we can use that to kind of cycle through our different materials. Let's take a example of this. So we continue with our example from sodium phosphate and barium chloride from earlier. And these guys are all salts. You notice that we've already decided who's aqueous, who's aqueous, who's aqueous, and who's the solid inside of here. And so when I go through and think about my solubility rules and that sort of thing, what I find out is if I go and think about my sodium phosphate, for example, if I go to my flow chart and I think about my flow chart, what will happen is in my flow chart I'll find out that sodium phosphate is soluble and it's a strong electrolyte. So is barium chloride. So is sodium chloride, but barium phosphate is not. So as a result of that, I'm going to take and break my sodium phosphate up into its component ions, break my barium chloride into its component ions, and break my sodium chloride into its component ions. So I'm going to leave barium phosphate where it was. Okay, I'm not going to change that at all. And so when I come down and write these out, notice when I break this into ions, if I ignore the 2, I've got sodium phosphate has 3 sodium ions and a phosphate ion in it. So if I multiply it by 2, it has 6 sodium ions in it, and it has 2 phosphate ions in it, and it looks like this. So I continue that process through for my barium chloride, my sodium chloride all the way over here, and this is my total or complete ionic equation. Now, if I want to get rid of the spectators, they don't do anything, so why mess with them? Why complicate things? I look at the equation and say, well, who didn't do anything? 6 sodium ions here, 6 sodium ions over there, boom, they can cancel those out. They're the same on both sides. I look at my 6 chloride ions here, 6 chloride ions right here, they're the same on both sides, boom, I can cancel those out. What I'm left with is 2 phosphate ions and 3 barium ions give me barium phosphate. That is the guts of this reaction. That's what happens, and that's the most important part for us to be able to understand that. As you move into Chem 2, being able to get rid of spectator ions is vital in these solutions, otherwise you'll go absolutely nuts. Flowchart, again, skip because I forgot to do something else with it. And over here, just some ideas about troubleshooting your equation writing to pay attention to. If you're completing and balancing a metathesis reaction, make sure you write the formulas for the products based on the formula writing rules. Don't drag across how many you have on the left and how many you have on the right. You'll take care of that in balancing. If the balancing when you get done seems to be really difficult, you better go back and check your formulas because that's usually where you have a problem. Okay, so make sure your formulas are right or else you'll have issues. And then in the case of complete ionic and net ionic equations, what I think about in here is be sure your starting equation is balanced. You're going to use only species you're going to separate only species that are both soluble and strong electrolytes. Those are the only ones you're going to separate into ions. And then you're going to include the charges in all the ions that you write. Okay? And on top of that, you include the states, whether they're in solid, liquid, gas, or aqueous. And the other thing you can do too is you can check your balancing by looking at the charges. So in the previous example, we had we had 3 bariums. 3 bariums, each one is 2 plus charges, that's 6 pluses. We had 2 phosphate, each 3 minus, so 2 3 minuses is 6 minuses, 6 pluses, 6 minuses is 0. The right-hand side also had 0, so that equation is balanced. I hope that helps, and I hope you get a lot of practice writing your net ionic equations in this particular experiment. Thank you.